Hello.
Hi. Hello.
It got cold quick, didn't it?
Hello.
Whole lot colder now than it was.
I know. The wind, like it's so windy.
Is it? I haven't been outside yet today.
My
Right.
I don't
feet,
have many trees around my house, so that may also be my issue. But it's very windy.
my feet have not stopped being numb.
It's kind of nice to have fall here though. I was getting tired.
No,
Okay.
yeah. Yeah, last night and this morning I was outside, so it was rough. But
Yeah. Well, I'm glad everybody made it here today.
yay.
I'm
How are you feeling?
doing okay. I'm
Good.
all right. I have a treatment next Friday, I think. Unless they're able to move it up, it's going to be next Friday, and then we'll
Okay.
go from there. But thanks for asking.
Always.
And let's see. I think today we were going to. We talked about the multiplication rule, and we were going to extend that out to what we called conditional probability, which is really just taking the multiplication rule and doing a little algebra 1 step on it and rewriting it in a different way to handle different types of problems. So it's not a whole new topic, but it is. And I just remember it well because I really struggled with the problems when I was in your seat and the way they were worded and all that. And I've just managed to teach myself over the year to be deliberate, follow the steps, don't try to outthink it. Just put it together a piece at a time, and then it's really not a problem. So we'll see if I've learned anything in all these many years. Let's see. The formula was for the multiplication rule, but it was specifically for dependent events. So 2 things were happening, A and B, 2 events were happening. One followed the other, and the first one happening affected the probability of the second one. So they're not independent events, they're dependent events. So since they're dependent, the formula will look like this. The probability of A and B occurring, just 2 separate events, is the probability of A occurring times the probability of B occurring, and this is just notation here, this little vertical line, given A has already occurred. So that just helps us remember, hey, wait a minute, B is occurring, but something just happened and it affected B. So we have to account for that. And the simple ones we did were drawing cards out of a deck. You draw 1 card out, and that makes the deck a little bit smaller. So that's a simple example of that. And you get into more complex examples, but the math doesn't have to be complex. And I think maybe that was my problem. I overthought these things way too much. So anyway, multiplication rule. So when we look at this, the way we're going to look at it today, we often call it conditional probability because it's the first one happening sets a condition for the second one. You know, it's not just happening on its own. Something else has happened. We have, my teacher used to say, we have prior knowledge. Something just occurred. If you say, for example, what's the probability of a 16-year-old having a car accident given he is male? Well, the fact that he's male does change things of having car accidents, especially for teenagers. The statistics show that boys have accidents in much higher numbers than girls. So here I am beating up on boys again, but just don't tell anybody. But it's just true. And insurance rates prove it. So that prior knowledge, you know, insurance companies are very interested in that. Anyway, what I want to do is separate out this one term. And I do that through simple little algebra 1 step. Right now, the probability of B given A, is multiplied by the probability of A. So to get it by itself, all we do is that little thing we used to do where we divided both sides by the same thing. So if I divide this on both sides, then this cancels over here. And what I'm left with, I'm going to flip this over a little bit. I'm going to write this side down first. So this is the formula as it's rewritten. But it's easy to come up with. You can always just start with the multiplication rule for dependent events and do this one little step. And you have this as a result. So this will be the formula that we are interested in here. And it yields some pretty interesting results. It also says what we're going to need in order to find the probability, and this vertical line in this B given A is usually read as the word given. B given A has already occurred. So we kind of shorten that down to B given A. In order to calculate that, you have to have the probability of both A and B happening. And then you divide that by the probability of A. And that's another common mistake, is getting the wrong thing under here. Sometimes people, including me, accidentally slip the probability of B under there, but it's not. It's A. It's whichever one of these happened second, after we had some prior knowledge. So anyway, that's going to be our formula today. And we will grind out some problems with it. And if we get a chance, we'll watch a video about lie detectors. And we'll go on from there. I don't know if we'll have time for much else. And I'll probably slow us down through the lie detector video and talk about the different steps as we go along. I have to play it back at a slower speed anyway, because it's done by, the guy sounds like he's from England, and they talk really fast, and I'm from the South. I don't think that fast. I definitely don't talk that fast. So slow it down a little bit, buddy. So fortunately on YouTube, you can just slow this stuff down or I'd be in trouble. So here's what we're going to use. And we're going to go back through some problems just on the classwork problems that we had. And we're going to see how this works with them.
Mr. Ritchie,
Yes,
what's that formula called again?
I would file this under conditional probability. But it's really just the multiplication rule written a different way.
Mr. Ritchie.
Yes.
So because I'm not gonna lie, last class I was kind of sick, so I'm not gonna say I wasn't paying attention, but I wasn't paying total.
Yeah, I could tell you weren't. Bad.
Have you posted any classwork, or is the classwork you're talking about just the class practice that you've just been using to kind of show us?
Yeah, just the class practice. And I haven't posted the video from Monday, but that'll show us working through, if you were kind of out of it, that'll kind of show us working through those classwork problems.
Okay, and then the one that's, because I'm just kind of looking at it, and then the elementary probability homework, we haven't done that at all, right?
No,
Okay.
we're kind of plotting through this chapter.
Oh no, it's okay. I was just making sure.
Yeah, well, that's the one we'll do those next, and those are the ones that are more similar to the test. So those will be the ones that kind of prepare you for the look of what the test is going to be. This other stuff is just fun problems to do together with friends.
All right. Well, thank
Yeah.
you. It is fun. It's easier to do it by myself. So
All right, so we would call it conditional probability, and this would be the formula. In this part, we read this, probability of B given A has already occurred. And sometimes it's read shorthand. It's just the probability of B given A. You know, we like to shorten things in math because sometimes it's just a big mouthful to repeat over and over again. So let us, so you're feeling better? I don't know, you sound like yourself again.
yeah, I'm better. I really think it was just like the weather change. My immune system just kind of hates me sometimes. So
That used to always happen to me when it would finally get from warm to cold or cold to warm, I would get sick.
yeah, like I wasn't miserable, but it just, my nose was kind of stuffy.
Yeah, I could tell you were congested.
Yeah.
Not miserable, but definitely annoying.
Yes.
All right, let's flip over. So right now on Canvas, stumble my way there. Here I am. And of course, this is my view, so it's a little different than yours. But not a lot different. We're over down here to module 3. And this is what we've been working on, is just this class practice, which is something I didn't do in the first 2 modules. I just added it on this one because I feel like we have to talk about this probability a little bit more than some of the earlier topics. Then we will do this homework, which will prepare us for the test, which is hiding somewhere. I'll have to see what I did with that. I don't see it here, but it'll be here shortly. So anyway, here's where we are. And we already, the fruit survey and the coin flips simulator was just a little classroom discussion about how some data is from random events like flipping coins, and other data is not random. Asking people, or people choosing careers, or deciding what kind of fruit they like. Those are not random events. We have preferences, and that's great. All right, so back to now we'll pick through this. I know we've done some of them, but I'll be able to tell the new ones that we're going to do today. Most of them are set up in tables just because of the nature of the problems. Okay, we're good on that one. And sorry, this was just an old assignment I found, and I dumped it in here to give us some stuff to do. It's not organized very appropriately, so that's why I keep picking through it. I always, these problems are sometimes easy to identify because they have that word given in there. Notice we have kind of 2 things going on here. We have freshmen and sophomore students, and then that same group, we have it divided a different way, whether they're credit card carriers or not credit card carriers. So just looking at that table, of data up there. How many total students were asked in this survey?
100.
Very good. Here they are right here. So just reading these tables. And, if you counted them, this total, there were 37 credit card carriers and then 63 non-credit card carriers. That adds up to 100. There were 60 freshmen and 40 sophomores. That adds up to 100. But it's the same 100 kids. They just asked them two different questions. Two different questions. So what this question is, here's the group of students, and they're asked if they were carrying a credit card, and they determined what year in school they were. And they say now, here's this data we have. If we select a student at random, find the probability that he or she owns a credit card given the student is a freshman. Now, I like to be, like I said before, I used to make a lot of mistakes on these things for a variety of reasons, I'm sure. And I like to rewrite, let me see, I'm going to write the formula up here so it stays with us. The probability of B given A has occurred is the probability of B and A both being true, both happening, A and B, divided by the probability of A occurring. So that will keep me straight. So what I do, or what I like to do, is rewrite, for the particular problem, rewrite that formula. And instead of A's and B's, I use the actual events that were given in the problem. So find the probability that he or she owns a credit card given the student is a freshman. So I want to know the probability that the kid has a credit card given that student is a freshman. Now, this is where I would make my mistakes. Don't jump to an answer and look for a number that's under both the freshman and credit card column and all that. It's not that simple. It's not that simple. So we're asking, what's the probability the student has a credit card given some prior knowledge? And the prior knowledge is that student is a freshman. So you can't just jump to here and say, oh, there it is. So don't resist. Don't fall into the trap I did. And rewriting my formula on the other side, that would be the probability of being a freshman and having a credit card divided by the probability of freshman, right? Notice the A, the second thing goes under here. Does that first step make sense? How I got from here to here?
Yes.
Okay. Yeah. And that's just me being deliberate and doing the steps. And I still do that. And it drives my kid, when I'm helping my kids with math, it drives them nuts. They don't want to write steps down. But they end up taking more time trying to explain what they didn't write down. But I'll never get through to them. So anyway, first number we need to find in our table is what's the probability of a student being a freshman and having a credit card? How many students are both a freshman and have a credit card?
Would it be 80 students?
Well, it's freshman and a credit card.
Okay, so then
20?
20?
I mean,
Oh.
wait, hold on.
Yeah, I think they're
Could be
both right.
20.
Oh, it's 20.
Yeah, these are the
Okay.
students.
Oh, I see it. Sorry, I didn't even.
Oh, I thought earlier you said it wouldn't be that.
Well,
That's why.
that's not the end answer. No, this is not the answer.
Okay. I thought
It's
you were
just the
saying
numerator.
that's. Oh, okay. Then that makes sense.
That is not this. You know,
Okay.
we're not done. And that used to
Yeah.
be, forget me. I'm like, okay, there it is. I'm done. And not so simple, Brent, but in our time.
Yeah.
So that's all that is. That's just our numerator. Now, both of these are probabilities. So let me write them that way. It's 20 of those students. We're asking, what's the probability of having a credit card and being a freshman? You say, well, there's 20 students that fit that category divided by how many total students in the sample space?
For the freshman or
Just how many total students in the sample space?
100.
Right. See, that's what I also used to do, Lexi. I would start saying, well, we're talking about freshmen here, so the total
Yeah.
freshmen is 60. And that's, you have to really focus on the step you're doing. So right now, we're just looking at all the students, and 20 out of 100 are both freshmen and have a credit card. And we're going to end up with a fraction over a fraction, which is a little messy, but don't worry, we're going to be able to shorten this a little bit where we won't have to worry about it so much. Now, what's the probability of being a freshman? In our total sample space, our total 100 students, how many students are freshmen?
60.
And you got that from right here, right?
Mm-hmm.
That's your total freshmen. There's 60. You have 60 total freshmen divided by how many's in the sample space?
100.
100. So you're going to see this. I'll do the next problem this way too, but you can kind of start cutting corners. You're going to see this, I believe, on all the problems where we get a fraction over a fraction, but these two numbers are the same right here. And when you have a fraction over a fraction and the denominators are the same, they just cancel out. So we will be able to get a little lazier and just write that top number and not write, when we're doing this specific type of problem, we don't have to write the sample space twice because we know that's going to cancel out. Is that okay?
So the 100 is going to cancel out, you said?
Yeah, they cancel out. Whenever you
Okay.
have a fraction
Oh,
over a
yeah. Yeah.
fraction, they cancel out.
So what was the reason for the 100?
Because the formula says, what is the probability of being a freshman and a credit card holder? 20 is not a probability.
Yeah.
Probabilities are between 0 and 1. So to be true, to be accurate mathematically, the probability of being a freshman and having a credit card is 20 over 100.
Okay.
The shorthand, what we're going to eventually, we'll do a couple like this, but you're going to notice as we do them that these denominators are all, that here and here are always the same. So they're always going to cancel out. And so we'll skip past them, but it's not great mathematically. Is really the probability of being a freshman isn't 60. That doesn't make any sense. You know, probabilities are between 0 and 1, and 60 is not between 0 and 1. It's 60 over 100, but we'll get a little bit lazy and know that those two denominators cancel, and we just end up with this anyway. So if you'll allow me to make things a little shorter and save ourselves a little bit of time, then we'll kind of get into the routine where you don't, well, it's not a big deal to write those denominators, but you don't really have to. So what does that reduce to? You see our answers are all decimals.
I got the 0.333.
There we go. So the probability of a student, you draw a student from random, the probability that that student has a credit card, given he or she is a freshman, you have that prior knowledge, is 0.333. And these aren't always obvious conclusions. And you may think you found a shortcut for this particular problem by looking at the table, but be careful because sometimes that shortcut works only on that specific problem and it won't work the next time. So you have to be careful. It's really not that hard to do it out the right way. All right. Here's another one. I see my little given here, so I kind of am tipped off. And it says, okay, all the same things here. A group of students was asked if they carry a credit card. The responses are listed below. If the student is selected at random, find the probability that he or she owns a credit card, given the student is a sophomore. So probability of owning a credit card, given sophomore. And I think on this one, after we finish it, I'm going to do it and I'm going to reverse the order of sophomore and credit card to show you it's not the same thing. You get a different answer. The probability of owning a credit card given you're a sophomore is not necessarily the same as the probability of being a sophomore given you own a credit card. So the order is important. You have to make sure you get this in the proper order. And I'm just being careful when I write this. Credit card comes first. Owns a credit card given sophomore. So I'll write my little. So that's going to be the probability of being a sophomore and having a credit card. I'm just rewriting this formula up over here, except for instead of using B and A or A and B, I'm using the two events that I'm having in this problem, which is sophomore and credit card. Now, which one goes on the bottom? Probability of what?
It's the probability of sophomore.
Very good. You guys are not falling into the same traps that I did. I was
Yay.
special, I guess. Yeah. That's okay. I'm glad you're not. All right. Let me give you a minute just to see if you can put that together, and then we'll work it together in a minute. Okay, let's see how we did. First of all, I need to know the probability of being a sophomore and having a credit card. How many students satisfy both of those?
7.
Yeah, and you find that right here.
Mhm.
These are the kids that are sophomores and have a credit card. And then how many, since this is a probability, I'm trying to be good. How many total in the sample size? Not sample size, sample space.
40.
Well, no.
Oh, 100. Sorry.
That's okay. It's going to cancel it. Like I said, these are going to get canceled out anyway. But we're just trying to be good and write it like a probability. So to answer the question, what's the probability of being a sophomore and having a credit card? The answer to that question is 7/100. But that's just the first step in this little bit larger problem that we're doing. All right. And now the bottom, what's the probability of being a sophomore? How many sophomores do we have?
40.
40 sophomores. And that came from right here. Here's the total 40 sophomores. And how many total kids in the survey? In the sample?
100.
Still 100. So you can see that here again, these denominators match, so they end up just canceling out. And you say, well, why do you keep writing them down? Well, because the question was, what's the probability of being a sophomore? And the probability of being a sophomore is 40/100. So that's why I did it, trying to be good. What does that calculate out to as a decimal?
0.175.
So the probability of a student having a credit card, given that student's a sophomore, is 0.0175. And there's the answer there at the bottom. Now, just for fun, this is not the correct way to do this problem, but I'm just going to reverse the order to show you that it becomes a whole different problem. And I'll do it in a different color. So just for fun, we're going to say, well, couldn't I just do this? Couldn't I just do the probability of being a sophomore given I had a credit card? Hey, isn't that the same thing? And the answer to that is no, sir, it is not the same thing. Now, looking at that and writing, using my formula up here, that would become on the top, the probability of credit card and sophomore. Now, with the and statement, this logical and statement we have in that we write here, the order there is not important. The probability of A and B is the same as the probability of B and A, but we don't really need to go down that road. So our numerator probably not going to change here, but what goes on the bottom of this new problem? The probability of what?
Sophomores? No, credit cards?
Yeah, see, that's the difference right there. So when we flip the order of these two things from credit card given sophomore to sophomore given credit card, it changes that denominator. All right, so the numerator, credit card and sophomore, well, that's still these same 7 students. They have a credit card and they're sophomores, 7 out of 100. But now what does the bottom look like? The bottom looks like the probability of having a credit card. Total number of students that have a credit card are 22. There's 22 students that have a credit card. There's 100 students in the sample space. My answer now becomes 7/22, which is different. We had 7/40 here. Now we have 7/22. So the order that you do these is important. The probability of a student having a credit card given he or she is a sophomore is different than the probability of a student being a sophomore given he or she has a credit card. So be careful about the order because order matters. But the first way we did it is, let me erase this. Sometimes I hesitate to do things the wrong way, even to make a point, because I don't want anybody to get mixed up. But that's our answer to this question. I just wanted to demonstrate that you can't get lazy and just do whatever order you want. You have to be mindful of that. All right, let us is that one? That one? That one? And that one? I guess the point is we've worked quite a few problems here. I'm sure those weren't the only two. I say I'm sure, but now this one, look at first glance, this one looks like those other ones, but notice when we've already done this because the question asks or who's a man or a non-smoker. It doesn't ask a conditional probability question. It doesn't ask man given he's a non-smoker. So we did that. That was an or question that fell in the addition rule section. And there's these counting ones that I haven't got. Well, those were the only two. I feel cheated. Let us now watch this video together. And what we might do is just watch it and discuss it kind of lightly. And then on Monday, I'll break it down. And we'll look at it with the formula like a regular problem and kind of demystify it. And then you'll hear me complain about lie detectors again. So the thought of somebody being unfairly convicted of a crime just bothers, I know it bothers everybody. It just really bothers me. And you see now with DNA, which we're so fortunate to have, all these people getting, well, it's not tons of people, but some people getting released, having been in prison for 30 years for a murder. And now we know absolutely positively that person was not guilty, and having them released, it's such a tragedy. I just can't imagine how horrible that was for that person. So anyway, part of a way to avoid that happening to you is not to voluntarily subject yourself to a lie detector test, because that's a lot of times how it starts for some of these people. And then some of them, they fail it and then they're grilled. And the police and interrogators are very good at what they do. So they can really grind people down, and depending on the person, they can get them sometimes to confess to something they didn't do. And I know that seems unthinkable to some of us, but it actually happens, and it has happened. And then it's just tragic. Because not only is the wrong person in prison for 30 years, there's some murderer out there. You know, if my daughter was murdered, not only is a horrible tragedy of this person being locked up wrongly for 30 years, but then my daughter's murderer has been free doing whatever, who knows what, for the last 30 years as well. And that's just a whole nother tragedy. But anyway, that's why I always get stuck on this. Just the thought of it, it's terrible, I think. Let me play this video, and I think we'll just watch it. And I'm going to slow it down because the guy talks ridiculously fast. And well, for this Southern boy, he talks fast. And then I think we'll probably break it down. And it's available for you to watch. So you can rewatch. Oh, well, here it is. Let me make it available. Now it's available for you to watch. You can rewatch it between now and last class, but I'll break it down into numbers and I'll put them in tables like we had on those last two problems. And we'll work it through that way and see what they're saying. Has anybody in here taken a lie detector test before? Nobody?
Not me.
Yeah, I guess maybe this is another reason. I actually did take a lie detector test for a job I was applying for. And I have a problem with them because I don't think the truth is conditional. The truth is the truth to me. And it was with, I was interviewing with a national security agency, you know, a federal agency, a bunch of spies and stuff. They use a lot of mathematicians. And I was finishing up graduate school in mathematics. And in graduate school, especially in math, you have a lot of foreign-born classmates. A lot of the faculty too, most of the faculty, but also the classmates are very diverse. So when I was first of all, it's a very high pressure situation because they put you in a chair in this room and face you one of those two-way mirrors. So you know there's somebody watching from the other side. And they hook you up in everywhere around your waist, your arms, and your head. And the guy stands behind you and asks questions. And then sometimes he repeats the same question, which implies that he didn't like your answer, had an issue with your answer. And he asked me, had I been in contact with foreign nationals, any foreign nationals? And of course, being NSA, they're concerned about people working at NSA having some sort of relationship from people with other countries and maybe getting in trouble, and those people from those other countries having some sort of blackmail material and being able to get secrets out of them. And that's their concern. But his question was, have you had any contact with foreign nationals? And of course I did. Every time I had class, I had contacts. I had friends in my class and contacts in there from different countries. So I said, yes. And he said, okay, explain that. And I told him, well, in my class, I have these classmates and they're from foreign countries. He said, okay, don't worry about them. And then he asked the same question again. Well, just some guy telling me not to worry about it didn't change the answer to the question to me. When he asked me, did I have contact with foreign nationals again? Because he asked it in the exact same way. My answer is the same. And then it became very combative and it was a very unpleasant experience. So, but anyway, that's more than you wanted or needed to know about that, I'm sure.
That's frustrating.
Yeah, oh, it was extremely frustrating for me. Because the
I would
truth is
hate
the
that.
truth. Yeah. To me, the truth is the truth. I had
Yeah.
now, if he'd have reworded the question and said, except for the ones in your class, have you had any, you know, if he'd have done it like that, I could have answered differently. But I think because of the way they test, they have to ask the question the same way. And just some guy telling me something's not a lie in my mind does not make it not a lie.
Yeah.
It's still, they don't get, another person doesn't get to do that.
Yeah.
Like I'll say, like me telling Lexi, okay, we're going to go in this convenience store and it's okay for you to steal a candy bar. It's okay. You know, that doesn't really, just because I tell you that doesn't change it. You're not going to go in there and, just because I said it was okay.
Yeah.
So anyway, all right, let me try to play this through once and we might talk about it a little bit, but I just want you to really digest it, and then we'll break it down next class. And let's see, I think I can slow it down to 1.25 without it being too.
I think 1.25 speeds it up.
All right, that's why I got you all in this class, because I do old man stuff. Let me try 0.75 and see how that plays.
Imagine if you had a lie detector that was able to detect truth or lies 9 times out of 10. You'd nearly always be able to tell if someone was telling the truth or telling a lie. How brilliant would that be for solving crimes or finding out who ate the last cookie without telling anyone? Let's put aside the question of whether or not people can learn to beat lie detectors by pinching themselves or learning to imagine relaxing on a beach while answering your questions, and assume that the lie detector is going to be equally accurate with everyone who takes a test. That means all you have to do is wire someone up to the lie detector, and if the big red lie light flashes, then you're 90% sure they're lying. Fantastic. But wait a minute, we've forgotten some basic conditional probability here. A test being 90% accurate is not the same thing as being 90% certain that someone is lying if the machine says they are. If the lie detector is 90% accurate, then it correctly identifies 9 out of 10 lies as lies and incorrectly says that 1 out of 10 lies are true. It'll also correctly identify that someone is telling the truth 9 times out of 10 and incorrectly accuse them of lying 1 in 10 times. This is all well and good if everyone tells the truth or lies in equal measure. But in reality, people tell the truth far more than they tell lies. For the sake of argument, let's say 90% of statements are true and only 10% are lies. Now let's imagine an experiment in which we do 100,000 tests and see what happens when we sum up the results in a table. In 100,000 tests, 90% of people tell the truth. That's 90,000 actual true statements and 10,000 actual lies. The lie detector says 90% of the actually true statements are true. That's 81,000, but it wrongly identifies 10% of those true statements as lies. That's 9,000 false accusations of lying. It correctly identifies 90% of the 10,000 lies as lies. That's 9,000, and wrongly says that 10% of the lies are true. 1,000 lies that slip through the net and are believed to be true. So the lie detector thinks there are 82,000 true statements and 18,000 lies. It's underestimated the number of true statements and overestimated the number of lies. Overall, it correctly identified 90,000 of the statements, which makes it 90% reliable. But here's the all-important thing. The lie detector accused 18,000 statements of being lies, even though only 9,000 of them actually were lies. If it accuses you of lying, there's only a 9,000 out of 18,000 probability that you actually are lying. That's a half, 50%.
So that part shows you that if the lie detector test shows you're lying, in that case, it's only correct half the time. So if you fail a lie detector test, based on the probabilities they gave us half of the time, that's incorrectly identifies you as lying. And I'll let this keep playing through. And like I said, I'll break it down more next class.
Even though it correctly labels 90% of the statements truth or lie, it's no better than flipping a coin at predicting whether you're telling a lie. The problem is people actually telling the truth, incorrectly allocating 10% of a large number of true statements as lies completely messes up the results. We need to be quite subtle about how we use the test. If it says you're lying, then the 90% reliability rating is not relevant. We need to consider the whole story, including the prevalence of lying in the whole population and the number of true statements that the test has mistaken for lies. In this case, we found that leads to the conclusion that it's only 50% likely you're lying if the test says you are. Back in the 1700s, the Reverend Thomas Bayes proposed a formula, which we now call Bayes' theorem, that helps us to work out conditional probabilities. It applies in all sorts of situations like lie detector tests, medical screening tests, criminal investigations, email spam filtering, crash wreckage location, and many more. The probability of A given B equals the probability of B given A times the probability of A all over the probability of B. It's well worth learning more about so you can make more informed decisions the next time you want to know who ate the last cookie. Or your test results seem to say it's 90% likely you've got lurgy disease, or you want to know why your spam filter is making bad decisions about your emails. When you subscribe to our channel, remember to click the bell to.
All right, and that's a lot of numbers thrown out there at one time. So I know it's a little hard to follow, but between now and next class, maybe try to watch it again. But I will break down all those numbers into tables so we can work through it like we did those other problems, taking our time and working through it slowly. And then you can see, I think, more of what's going on there. And like he said, it also applies not only to the lie detector test, but the same ideas apply, to spam filters and other things. So it's kind of an interesting topic to be aware of. So I think that's what we'll do for today. And then Monday, we'll talk more about that particular problem. And like I said, you can watch it again if you want to, but I'll try to break it down in detail so we can discuss it a piece at a time, because it is really interesting, or at least I think so. But I appreciate you coming today, and I've received texts between Monday and Wednesday from students in this class, and I answer them. So I'm always available between classes if you need me for anything. There's nothing due. There's no tests out there. The practice homework will probably get started on that Monday as well. So maybe even get through that. I don't know. And
I have
then
a question.
Sure.
Is this Zoom gonna be on YouTube? I'm probably gonna watch it again just to like get everything. Are you gonna post it on YouTube?
Yeah, I'm going to post it like I posted these other ones. I have Monday and Wednesday both.
Okay,
Which
thank you.
I put the link in here, but you are right. I'm actually dumping it to a YouTube channel I have. But
I usually just go straight there because it's just
Yeah.
easier.
Yeah, the only problem, and that's perfectly fine, but that channel is just is not organized at all. If you've been there, you've seen it. I'm just dumping stuff from multiple classes there. So it's not really set up to navigate very well, but I will upload it there and then link it here so you go to the right one, but feel free to watch it there if you want to. So I'll
Okay.
put both Monday and Wednesday's class up here before too long. Okay, any other questions? All right, you guys have a great weekend, and I will see you Monday.
too.
Thank
Bye.
you.
Bye, everybody.
Have a good day.
You too.
Bye, Mr. Ritchie.
Bye.